So let's take a look at a definition of entropy that allows us to think about this idea of microstates really well. And this is Boltzmann's definition of entropy. So this is super, super important. And in fact, if you go look up Boltzmann's gravestone, he has this actually on his gravestone. The notation's slightly different. He uses a W instead of an omega, but that's how critically important this definition of entropy is and this equation is that this is kind of the thing that he is perhaps best known for. The Boltzmann distribution is also pretty famous, but Boltzmann defined entropy in terms of this number of microstates. Okay, and so before this time, entropy had been thought of in this very ambiguous sort of way where it was just sort of this value of an energy change and stuff, and it was pretty nebulous. But what Boltzmann did is he took that definition of entropy and he turned it into something that is statistically easy to think about. Not necessarily easy to calculate, I'll be totally honest. Number of microstates can be pretty complicated, but it's pretty easy to think about. And so if we think about Boltzmann's definition, he said entropy is equal to K, which is called Boltzmann's constant, times the natural log of, we're going to use the notation omega, and omega is that number of microstates of the system. And so you can see pretty clearly as the number of microstates goes up, so does the entropy, right? And so that gives us that idea that we were talking about in the previous video. And so let's take a super crazy simple example. We're going to take a 2x2 checkerboard that has 4 checkers on it. And those 4 checkers can have one of 2 possible colors, right? That's how checkers work. And we're going to think about what are the possible ways for us to arrange the system. In our little model system here, we are not going to be allowing the checkers to move, right? So we don't have any kinetic energy of the checkers. We're just going to have positions that we're dealing with. But it gives us a pretty good idea of what we're talking about in terms of the statistical definition. So if we only have one kind of checker, we put one in each spot, we're done, right? That's it. There's only one way to arrange the system, one possible microstate. I could switch 2 of those checkers, but it doesn't look any different. It's the same microstate, right? So we have one possible microstate for this system. If I have 3 of one kind and 1 of another kind, though, I have far more possibilities, right? So in that case, I could have the one that is different in 4 different places. And these microstates all look different. They're all unique. If I flip 2 of the blue checkers, it still looks the same as one of the other things we have. But if I move that white checker, it looks like a different microstate. So in this case, we end up having 4 different microstates that system can have. If I keep going and I have 2 of one kind and 2 of the other kind, as it turns out, there's 6 different ways to arrange this system now, right? And so you can see them here. You can try to think of others. You won't. These are the 6 unique ways to arrange the system. And so I would have 6 microstates in this case. If I kept going and I switched one more out to be a white checker, I'd be back to 4 microstates, right? Because I would end up with something that looks more or less like this, but just flip which ones are which. If I go all the way to having all white ones, I would basically be back to having just 1 microstate. So the maximum number of microstates I can have in a system like this is to have 50% of one type and 50% of another type. And as it turns out, that ends up being true for things like gases as well. Your most entropic mixture is 50% of one gas, 50% of another gas. Anyway, so this gives us an idea of what we're talking about in terms of microstates. The more ways that we can arrange the system, the more microstates there are, and the more entropy there is in that system. All of these look really ordered to me. I don't see a difference in terms of that idea, right? But we have more ways to arrange the system when we go to having 2 blue checkers and 2 white checkers. So that would be our more entropic system. Okay, so if we think about this from the perspective of our entropy being a state function, so we worry about the entropy of the final state minus the entropy of the initial state, and then we plug Boltzmann's definition into each of those. Okay, so the entropy of the final state would be K natural log of omega F, so that's the number of microstates of our final state, minus K natural log of omega I, so that's the number of microstates of our initial system. We can play games with the natural logs, right? Remember, natural logs can be combined, and so I have a difference in natural logs, which becomes the natural log of the ratio, right? So our argument becomes the ratio of the number of microstates. And so we can think about this change in the entropy then as telling us about what's happening to the number of microstates. So if I have an increase in the number of microstates, so final is greater than initial, this is going to be a number that is greater than 1. The natural log of a number that is greater than 1 is a positive number. And Boltzmann's constant is a positive number. It's just a constant, right? So we end up with an increase in entropy. And so that's how you can connect this statistical definition of entropy to this idea of the microstates. As the number of microstates go up, my entropy is going to increase. If the number of microstates go down, so my final number of microstates is less than my initial number of microstates, I'm going to end up with a number in this ratio that is less than 1. The natural log of that is going to be a negative number, and so my entropy is going to be decreasing in that particular case. So processes that lead to an increase in entropy, delta S being positive, we've already talked about one, right? Going from the solid to the liquid phase, so from something less entropic to something more entropic. We could go from the liquid phase to the gas phase. That's definitely going to be a huge increase in entropy because we're going from something with sort of moderate entropy to something with a very large entropy value. If we go straight from the solid phase to the gas phase, that's going to be an even bigger change in entropy. And in fact, if you knew the change in entropy for these first two quantities for that particular substance, whatever it was, you could add them together to get the change in entropy here. Because again, entropy is a state function. Remember, when something is a state function, I don't really care what the path is that I use to get from starting point to ending point. All I care is that I get from starting point to ending point. So if I added these two processes together, that's really the same thing as this third process. So you could do that for changes in entropy, just like you did for changes in enthalpy. One that we haven't really talked about yet is if we go from having a solute and a solvent separated, not mixed together, and then I put the solute in the solvent and it dissolves, that's going to be an increase in the change in the entropy as well, right? The solute is probably, it could be in the liquid phase, but let's assume we have a solid solute. Those particles are in that rigid structure. They're kind of confined to a very particular space, right? They can't move very much. When I put them into the solvent, they break up into pieces and we get these ions floating around in solution, right? And so I have a huge increase in the entropy because I've got these things that were in a rigid, tight structure in a larger volume and free to flow. And so that's definitely going to be an increase in entropy when I take a solute and put it into a solvent. It's also true if I take a solute that's a liquid and put it into a solvent. It's just less dramatic because we're not going from that rigid structure that you have in the solid, but it still would end up being an increase in entropy because I have more different kinds of particles in the same system and they're free to flow and be in a lot of different places. The other thing that we've talked a little bit about in the previous part is that an increase in temperature is also an increase in entropy. And so if I go and I increase the temperature, we need to remember that when I increase the temperature, I'm changing that distribution of the kinetic energies, right? So I'm going from something that perhaps looks like that to something that looks like this. So number of particles over here, kinetic energy here, right? Low temperature here, higher temperature here. And so as my temperature goes up, I have a larger distribution of kinetic energies that the particles can take on. That larger distribution of kinetic energies ends up meaning that I'm going to have a higher entropy. And so that increase in temperature ends up meaning an increase in entropy as well. Okay, this last picture down here is meant to represent what's happening in the solid phase as you have an increase in temperature. It's a little hard to sort of show this in a static picture. But the left-hand side here is meant to represent being at pretty low temperatures where basically the molecules are very stuck in their rigid spot. They can't really move at all. As I increase the temperatures, my kinetic energy distribution is going to go up, but they're still more or less constrained to be in pretty close to the same positions. But you can see that the microstates are going to be a little bit larger as I have a little more kinetic energy. So the molecules or the atoms are wiggling around a little bit in that solid structure. And so you get slightly different microstates that you can see. If I go to significantly higher temperature, you can see that those particles are moving out of that structure quite a bit. Not quite enough to call it liquid phase yet, but that increase in temperature is going to cause there to be more possible microstates because the molecules can move more. As I increase the temperature, even in the solid phase, you have more movement, right? And the kinetic energy is moving. If I went a little bit farther on my temperature scale here, and I don't think we're far from it in the way they've drawn this picture, those would be moving so much that you would actually end up breaking those interactions enough that you would end up in the liquid phase. So if we went just a little bit further in this picture, in this increase of temperature, you would end up in the liquid phase.